I'd like to provide some background on those two measures here, the standard deviation and the sample variance. The standard deviation is a measure for the dispersion of the data. So what we see when we have this histogram here, we see that the data is distributed and how it is distributed, but we would like to summarize that dispersion that we see here in a single number. And the result will be, as you see here, 70,000. I will interpret that number in a video on the rules of thumb. For the time being, I'd like to explain and show you what's going on behind the computation of that number. Both numbers, the standard deviation and the variance, are based on deviations from the mean. And in order to show you what's going on here is, let's first compute deviations from the mean. Okay, so we have a sales price minus the mean, and I'll fix the mean here by pressing the button F4, and now I can copy that cell by double clicking, and we see for each and every entry here we find deviations from the mean. Now it would be tempting and obvious somehow to say, well, let's try to summarize these deviations from the mean, for instance by computing the average. However, that average is always zero. So when we compute deviations from the mean first, and then compute the average of deviations from the mean for every data set, we would always get an average or a sum of zeros, by definition. So in order to get such a summary measure now, we would need to do something about that. And what happens now is the following. You take, for each and every deviation from the mean, the square. This is a large number, and not only that, it's a number which is now measured in terms of the square of the original data. So if this is in dollars, the price is in dollars, then the deviation from the mean is also in dollars, but the square of the deviation from the mean is in square dollars, which is not a meaningful number. But one thing is clear: if we compute the average of that deviation from the mean squared, we do get a positive number, not a zero as before. And this number is actually the variance. The main drawback of the variance is it has very strange units of measurement, always the square of the original units. And that's why we take the square root of that number to get rid of the squared units, and we end up with what it's called standard deviation. So, in other words, the standard deviation summarizes the dispersion of the data in terms of the squared deviations from the mean, takes the average of those squared deviations and takes the square root. The standard deviation can be directly computed with the function standard deviation, referring to the data range. As you can see, there's a slight difference between the result of taking the square root of the average of squared deviations from the mean and the standard deviation function. But that's due to a reason which I will explain later in a video on the properties of estimates from a sample. For the time being, we should remember that the standard deviation is a measure for the dispersion of the data around its mean, and it is measured in the same units as the original data, in this case dollars. A further interpretation will be provided in the video on the rules of thumb.